Now it's my turn to present our work entitled Broadband Cnoidal Waves and Influence of Third-Order Dispersion and Self-Steepening Effect. My name is Aneliya Dakova, and I'm from the Institute of Electronics at Bulgarian Academia of Sciences. I'm sorry for the technical issues, but now we are ready to continue. So in the last few decades, the investigations of the behavior of phase-modulated femtosecond and attosecond optical pulses is one of the most rapidly developing scientific fields in modern optics and laser physics. Attosecond and phase-modulated femtosecond optical pulses have few oscillations of the electrical field under their envelope. So the processes that are shortening the time duration of optical pulses actually lead to their spectral broadening. The effects resulting from the evolution of broadband optical pulses in isotropic nonlinear dispersive media, such as optical fibers, are being actively studied by the scientists. So one of the most commonly used equation in optics is the nonlinear Schrödinger equation, which is derived for narrowband optical pulses. Such optical pulses have nanosecond and picosecond duration. They are naturally long, but in the frames of ultra-short optics, when the time duration of the optical pulses is less than 1 picosecond, the nonlinear Schrödinger equation is usually modified by adding terms that govern the higher order of nonlinear and dispersive phenomena, such as third order of linear dispersion and self-steepening effect. What is a third order of linear dispersion? This is a higher order dispersive phenomenon that has to be taken into account when we work with ultra-short optical pulses, even when the group velocity dispersion is different from zero. As a result, the shape of the pulses become asymmetric with oscillatory structures on one of their edges, depending on the sign of third order of dispersion. As you can see here, the intensity falls to zero in these deep oscillations when the group velocity dispersion is zero. Self-steepening effect is a higher order nonlinear effect that results from the intensity dependence of group velocity and leads to asymmetry in the shape and spectrum of ultra-short optical pulses. Their peaks shift toward the trailing edges, moving at lower speed than the wings. As a result, in optical fibers with low losses, we could observe an optical shock wave. So, as I already mentioned, the nonlinear Schrödinger equation very well describes the slowly varying amplitude function of the envelope of narrowband optical pulses, but it has some limitations. When we work with femtosecond and attosecond optical pulses, it is more convenient to use the general nonlinear amplitude equation, which works very well for long as well as ultra-short optical pulses. It differs from the nonlinear Schrödinger equation with these two non-paraxial terms here. As you can see here before the brackets, we have a multiplier, and on this table here, I have presented the value of this multiplier for laser pulses with different time duration. As you can see, when we have ultra-short optical pulses with 15 or 5 femtosecond, this multiplier has a significant value, and the expression in the brackets has to be taken into account. In this equation are included parameters connected with the number of oscillations under the envelope of the optical pulse. This is this parameter here, alpha. Gamma and gamma 1 are connected with the nonlinearity of the medium. Beta 2 is the group velocity dispersion. Sigma gives the relation between third and second order of dispersion. And we will work with optical pulses propagating in optical fibers with normal dispersion. In order to find a solution of our basic equation, we make the following substitution here, where A and B are constants about to be found, and F is a new unknown function. Our theoretical model requires to equalize the real and imaginary part from both sides of the obtained equality. And as a result, we reach to this system of two differential equations. As you can see, they are of the same type and they are referred to the same unknown function. So they should fully match. By equalizing the multipliers before the third order of f, we get to this equality here, from which we can find an expression for the constant a. In the same way, by equalizing the coefficients before f, we find this equality here, from which we have found an expression for the constant b. After the two constants are defined in a way that the system of equations fully matches, the equations 5 can be presented as this nonlinear equation of second order and third degree. If we make these assumptions here, it turns out that the equation 8 is of this kind here, where k is a parameter that has values between 0 and 1. This equation has a well-known solution in the form of periodic cnoidal wave. In our case, this is a Jacobi elliptic sine function. And considering the assumptions from the previous slide, the solution of equation 8 is given by Jacobi elliptic sine function as follows. And at the end of our theoretical model, going back through all the assumptions and substitutions that we have made by now, the following solution of the normalized nonlinear amplitude equation is obtained. It is in the form of a periodic cnoidal wave in the form of Jacobi elliptic sine function. So what are periodic cnoidal waves? They're usually presented by Jacobi elliptic functions, and these two types of equations has these solutions here. The first one gives the Jacobi elliptic sine function presented here on the graphics by the blue line. The second one is a Jacobi elliptic cosine function given by the red line. And the last equation has a solution in the form of Jacobi elliptic delta function presented by this yellow line here on the graphic. Here it is important to mention that the self-steepening parameter is equal in 1 in the way that in that way we have presented these graphics of periodic cnoidal waves for different values of the parameter k. We consider the evolution of light pulse with carrier wavelength of 800 nanometers in optical fiber with these parameters here. When the modulus of ellipticity is equal to 1, our cnoidal wave is reduced to a dark soliton. So the soliton solution of our basic equation has this form here. Having in mind that expression, an initial intensity condition for light pulses can be presented as follows. Here, this expression gives the initial intensity needed for the observation of dark soliton in the frames of a nonlinear amplitude equation. This expression here is connected with the initial intensity needed for the observation of dark soliton when we work with the nonlinear Schrödinger equation. This second condition here gives the correlation between the parameters of the optical fibers and those of the initial laser pulses for which actually a dark soliton can be observed. When the modulus of ellipticity is equal to 1 and when the constant h1 is equal to 2, we reach to this nonlinear dispersion ratio. So what are the solitons? My colleague Zara Kasapeteva will explain about them in details, but I will make a short introduction. Solitons are stable wave packages that are a result of the dynamic balance between dispersion and nonlinearity of the medium. Regarding to the dispersion, we can observe two types of solitons. Bright one when the dispersion of the optical fiber is anomalous, and dark one when it is normal. The bright soliton is obtained when we actually have this anomalous dispersion plus Kerr type nonlinearity, and dark solitons are characterized by this deep gap of intensity where it can falls to 0 for black solitons, and it is different from 0 when we have gray one. So as already mentioned, when the modulus of ellipticity, our solution is reduced to a black soliton. Here on this figure, you can see the typical intensity profile of ultra-short black soliton with broadband spectrum propagating in single-mode optical fiber. The initial time duration of the optical pulse is 2 femtosecond, and it has 4 oscillations under the envelope. And now I'm going to present you our calculations based on an optical fiber with anomalous dispersion. We use the same nonlinear amplitude equation, but here the sign of the dispersion is different. We use the same mathematical algorithm. So the solution of this equation is again in the form of periodic cnoidal wave, but this time in the form of Jacobi elliptic delta function. Here you can see these expressions presents the constants here in the solution. So when the modulus of ellipticity is equal to 1, again, our solution is reduced to a soliton, but this time into a bright soliton. And when the constant H2 is equal to 2, we can find the initial intensity condition needed for the observation of bright soliton. When we take into account this condition here, we can find the correlation between the parameters of the optical fibers and those of the initial laser pulses for which a bright soliton could be observed. And this is our new nonlinear dispersion ratio obtained when the modulus of ellipticity is equal to 1 and the constant H1 is equal to 1. So here you can see a graphics of periodic cnoidal waves for different values of the parameter K. We consider an optical pulse with a carrier wavelength of 1.45 microns propagating in a silica single mode fiber with these parameters here. When the modulus of ellipticity is equal to 1, the solution is reduced to a bright soliton. You can see this typical form of the bright soliton. This pulse has 7.5 femtosecond duration, and it has 4 oscillations under the pulse envelope. Why cnoidal waves are so important? Because their applications cover different scientific areas from hydrodynamics to optics. As you can see here on these pictures, cnoidal waves are observed in nature. They are in the form of clouds in the sky or waves in oceans and rivers. So in our investigations, we studied the propagation of optical pulses with broadband spectrum in single mode optical fibers in 2 different cases, when the dispersion of the optical fiber is normal and when it is anomalous. It was shown that for laser pulses with few oscillations under the envelope, the influence of third order of dispersion and self-steepening effect is significant, and these effects were taken into account in the nonlinear amplitude equation, and new analytical solutions in the form of Jacobi elliptic functions were found. The solutions present periodic cnoidal wave in the form of Jacobi elliptic sine function in the case of normal dispersion, and Jacobi elliptic delta function for optical fibers with anomalous dispersion. When the modulus of ellipticity is equal to 1, the corresponding solutions are reduced to optical solitons. Jacobi elliptic sine function is transformed into dark soliton, and Jacobi elliptic delta function into a bright soliton. The solutions lead also to a new kinds of nonlinear dispersion ratio, which involve 2 additional dimensionless parameters. Alpha is connected with the non-paraxiality of our theoretical model, and sigma characterize This is the relation between group velocity dispersion and third order of dispersion. These two parameters significantly affect the modulus of ellipticity. The initial conditions for formation of optical solitons and the connection between the parameters of the fiber and the pulse were also presented. The figures give the corresponding cnoidal waves and solitons. The obtained results have application in many scientific fields, and they are really important for modern communication systems to better understanding the transmission of optical signals over long distances. At the end of my presentation, I would like to thank for the support of the Bulgarian National Science Fund and the Ministry of Education and Sciences by these two grants. Here, on this picture, you can see part of our scientific team. This photo was taken a couple of years ago when the Nobel Prize winner in physics, Professor Gerard Mourou, was in Bulgaria. And of course, I would like to thank you for your